Pluto is a remote and bewildering, more unpretentious planet that was once a portion of our solar system's planetary meeting. However, later astounding announcements by prominent astrophysicist Neil deGrasse Tyson and others have brought Pluto back into the spotlight with an astonishing discovery. They suggested that this cold world is on a potential impact course with Neptune. But how could that be? This could end up being a significant event. In addition, what might be the repercussions of such a giant collision? Are we witnessing an intriguing cosmic anomaly? Or is there something more to this upcoming massive conflict? As we analyze the potential outcomes of a Pluto-Neptune impact, Pluto, a former dwarf planet that got its new planetary classification in part due to its stunning orbit, remains a subject of interest and assessment in the cosmic community. According to recent calculations by leading experts, Pluto's orbit is dangerously close to Neptune's. Both Neil deGrasse Tyson and Michio Kaku have sounded the alarm about a potential collision between these two planets, which could pose a serious threat to Earth. How is such an event even possible? Unlike any other planet in our solar system, Pluto's orbit around the Sun takes an astonishing 248 years to complete a single revolution. Since its discovery in 1930, it has yet to complete one full orbit. But that's not all. Pluto's orbit is highly elliptical, moving in a vastly different manner compared to the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its extreme inclination. It is tilted at a shocking 17 degrees to the ecliptic plane, far more than any other planet. This inclination, combined with its elongated shape, adds layers of complexity to its orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect based on their usual positions in the solar system. This raises a natural question. Why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets and the intricacies of Pluto's orbital mechanics. Pluto's orbit was studied extensively after its discovery. Initially, astronomers sought to understand why its path was so different from the nearly flat orbits of other planets. The mystery deepened when it was confirmed that Pluto's orbit does indeed cross Neptune's. Despite this, Pluto's orbit remains stable due to a phenomenon called orbital resonance. This refers to the gravitational effects between celestial bodies that prevent collisions. Specifically, Pluto and Neptune are locked in a 3:2 resonance, meaning that for every 3 orbits Neptune completes, Pluto completes exactly 2. This resonance ensures that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is critical in preventing a collision. Additionally, Pluto's highly inclined orbit means that when it comes closest to Neptune, it is actually above or below Neptune's orbital plane, adding another layer of protection. Another crucial concept is the cosine mechanism, named after the scientists von Zeipel, Kapos, and Litov, who studied the gravitational interactions of celestial bodies. It explains how 3-body interactions, such as those between Pluto, Neptune, and the Sun, can lead to long-term stability in seemingly chaotic orbits. In Pluto's case, the cosine mechanism helps us understand why its orbit, though appearing erratic, has remained stable for billions of years. While predicting large-scale cosmic events is challenging, mathematical simulations suggest that Pluto's orbit will remain secure for the foreseeable future. However, even slight deviations in orbital calculations can lead to vastly different long-term outcomes, emphasizing the complexity of celestial mechanics. This unpredictability is why prominent astrophysicists have recently raised concerns about a potential Pluto-Neptune collision. Despite the stabilizing forces at play, Neil deGrasse Tyson has pointed out that small gravitational interactions or external forces could introduce long-term instabilities. Tyson, who played a key role in Pluto's reclassification as a dwarf planet, views these orbital changes as an example of how much we still have to learn about our solar system. He emphasizes that as our understanding of celestial mechanics evolves, so too must our classifications and models of planetary motion. Another renowned physicist, Michio Kaku, offers a complementary perspective. Known for making complex scientific concepts accessible, Kaku highlights the unpredictable and often violent nature of cosmic interactions. He stresses that studying these orbital dynamics is not just an academic pursuit, but a crucial step in preparing for potential cosmic threats. The possibility of a Pluto-Neptune collision is not merely hypothetical. It reflects the ever-changing and dynamic nature of our solar system. As we continue to explore and refine our models of planetary motion, we may uncover even more surprises hidden within the vast mechanics of the universe. Kaku's futurist perspective urges us to remain vigilant in monitoring celestial interactions, emphasizing that even seemingly stable orbits can experience unexpected shifts over long periods. He underscores the importance of continued observation, advanced simulations, and deeper exploration of orbital mechanics to better predict and mitigate potential cosmic threats. The question remains, could Pluto's orbit truly destabilize enough to bring it on a collision course with Neptune? While current models suggest that resonance and gravitational influences provide a safeguard, small perturbations, such as interactions with other Kuiper Belt objects, passing stars, or even dark matter, could introduce unforeseen variables into the equation. One particularly intriguing possibility is the impact of undiscovered celestial bodies. Some astrophysicists have speculated that an unseen Planet 9, lurking in the outer reaches of our solar system, could subtly influence the orbits of Pluto and other distant objects. If such a planet exists, its gravitational pull might nudge Pluto's trajectory over millions of years, potentially altering its resonance with Neptune. Additionally, long-term simulations indicate that planetary orbits, while generally stable over short timescales, can experience chaotic variations over billions of years. The gravitational dance of our solar system is not a rigid, unchanging structure, but rather a dynamic and evolving system, subject to the laws of chaos theory. This brings us to another crucial aspect, the long-term fate of Pluto and Neptune. If, in some distant future, the gravitational forces that currently keep Pluto's orbit stable weaken or shift, the consequences could be dramatic. A direct impact between Pluto and Neptune would be a cataclysmic event, reshaping the outer solar system and sending debris scattering across interplanetary space. Such a collision could even have indirect consequences for Earth and other interplanets. While Pluto and Neptune are far from the terrestrial planets, the sheer energy of such an impact could eject fragments into unpredictable trajectories. Some of these fragments could eventually be pulled inward by the sun's gravity, posing potential risks to Earth and Mars over extended timescales. Beyond the immediate implications, a Pluto-Neptune collision would provide scientists with an unprecedented opportunity to study planetary formation and destruction in real time. By analyzing the debris, impact dynamics, and resulting shifts in orbital mechanics, researchers could gain valuable insights into similar events that may have shaped the early solar system. For now, however, Pluto remains locked in its intricate gravitational dance with Neptune, safely shielded from collision by the delicate balance of resonance and orbital mechanics. Yet, as history has shown, the cosmos is full of surprises. As our observational techniques improve and our understanding of celestial mechanics deepens, we may one day uncover hidden instabilities or new forces at play within our solar system. Whether Pluto's fate remains sealed within its current orbit or takes an unexpected turn, one thing is certain. The mysteries of our universe are far from fully unraveled. In the end, the potential collision between Pluto and Neptune serves as a reminder of both the fragility and resilience of planetary orbits. It highlights the incredible precision of cosmic mechanics, while also demonstrating the need for continuous exploration and scientific curiosity. As we stand on the edge of discovery, looking outward into the vast expanse of space, we must remain open to the ever-evolving nature of our universe, ready to adapt, learn, and embrace the unknown. Consider the broader repercussions of such occurrences. from their impact on our understanding of the solar system to the potential requirement for future interventions in space. This perspective highlights the importance of preparing for the unanticipated in space. According to Kaku, the more we grasp the forces at play, the better we will be prepared to navigate and potentially mitigate the effects of significant occurrences. Both Kaku and Tyson's viewpoints converge on the idea that space is an area of boundless discovery and that our current understanding, while significant, remains restricted. Their emphasis on the need for ongoing research and advanced modeling mirrors the growing nature of space science. They highlight the importance of not only understanding celestial mechanics, as they are now, but also speculating on how they might change in the future. The potential impact scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It emphasizes the need for robust scientific inquiry, modern technology, and the willingness to adapt our understanding as new information emerges. Tyson and Kaku assert that the mysteries of space, exemplified by Pluto's orbit, are a revitalizing call for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is widespread scientific agreement that, long into the future, the orbits of Neptune and Pluto will remain stable due to their mean motion resonance and the various gravitational forces acting on them. Therefore, a direct collision between Pluto and Neptune is incredibly unlikely. However, the intricacies and potential disruptions in orbital dynamics suggest that space experts should continue to monitor and learn more about these celestial bodies, understand their long-term behavior, and assess any potential dangers they may pose. While the likelihood of a Neptune-Pluto impact is theoretical and considered improbable with our current understanding, it underscores the importance of continuous review and observation in space science. Advances in technology, including more sophisticated telescopes and computational models, will assist astronomers in improving simulations and predictions, ensuring that we stay ahead of the dynamic and ever-evolving planetary system. Tyson's perspective on the renaming of Pluto and Kaku's emphasis on the unpredictable nature of celestial mechanics both highlight the need for continuous investigation and a flexible understanding of our universe. The potential impact scenario, while bringing out the dynamic and complex interactions within our nearby planetary system, ultimately reminds us of the vast, yet still murky spaces in our comprehension of space. Through continued investigation and observation, we strive to unravel these mysteries, ensuring that our knowledge stays in step with the ever-developing universe. Pluto continues to dazzle researchers and space enthusiasts alike with its remote and baffling nature. While its status as a dwarf planet has long been debated, its orbit and intriguing characteristics continue to captivate scientists. Recent developments have once again placed Pluto in the spotlight, with the potential for a gravitational interaction between Neptune and Pluto becoming the focal point of attention in the space community. With Kaku and Tyson bringing this topic to the forefront, the discussion surrounding a potential Pluto-Neptune impact is sure to spark more research and interest in the investigation of these enigmatic celestial bodies. Uncovering new insights into the mechanics of our planetary system is crucial. As we peer deeper into space, the dynamic and unpredictable nature of our celestial neighborhood only underscores the need for caution and ongoing investigation. While the potential interaction between Pluto and Neptune remains a topic of scientific interest, it is crucial to consider the broader context of space exploration and the methods used to study celestial bodies. The discovery of potential risks, such as a possible Pluto-Neptune impact, serves as a stark reminder of the immense unpredictability and complexity ingrained in the universe. It highlights the complicated mechanics at play within our local planetary system, where even the most stable-seeming orbits may harbor hidden vulnerabilities. This sophisticated thought is brought to attention by space-based tools and techniques used by experts and physicists to understand the movement of celestial bodies. One important instrument in these studies is mathematical simulations, which allows scientists to predict and model planetary and dwarf planet behavior over extended periods. By inputting known parameters, such as mass, speed, and distance of celestial objects. These simulations can project potential future movements and assess orbital stability. Such models often rely on powerful computers and advanced algorithms to handle vast amounts of data and complex calculations. This method is especially important when studying objects with irregular orbits like Pluto, whose path around the Sun is distinct from that of other planets in the solar system. Additionally, the role of gravitational interactions between celestial bodies cannot be overstated. As mentioned, Pluto's orbit crosses Neptune's, and the gravitational pull between these two bodies could hypothetically lead to unusual outcomes over very long timescales. However, due to the resonance between Pluto and Neptune, their orbits remain locked in a stable relationship.